welcome to the deep dive. Today we're digging into, well, maybe the biggest challenge in physics, trying to get quantum mechanics and general relativity to play nicely together.
It's a huge one. I mean, think about it. It's been 100 years since Schrödinger came up with his equation, a cornerstone.
Right, Schrödinger's equation. That lets us figure out probabilities for tiny quantum systems. The same Schrödinger with the cat, the thought experiment.
Exactly the same one. That equation is fantastic for the quantum world, the subatomic level. But then you've got Einstein's general relativity.
Which is all about gravity, space-time bending, brilliant for planets, galaxies, the big picture.
Perfect for the cosmos. So you have these two pillars of modern physics, one for the incredibly small, one for the unbelievably large, and they both work fantastically well.
But only in their own lanes, right?
Precisely. Try to use them together, say, to understand what's happening inside a black hole or right at the Big Bang, and things just, well, they break down. The math doesn't work, the descriptions conflict.
It's like they speak completely different languages.
That's a good way to put it. Quantum mechanics is all probabilities, fuzzy states. General relativity is smooth space-time, deterministic gravity. Oscar Varela over at Utah State University, he put that, well, you can explain lots of things with one or the other, but the explanations often clash.
So quantum gravity is the hunt for a translator, or maybe a whole new language.
Something like that, a single framework that holds both. And as Varela said, we honestly don't know what quantum gravity is yet.
Okay, so if it's such a puzzle, how are people actually trying to solve it? You mentioned Utah State University.
Right. That team, Oscar Varela, Abhay Katyal, and Ritabrata Bhattacharya, they're using a really interesting tool, an idea called the holographic principle.
Holographic principle? Okay, that sounds intriguing. Like a hologram.
Sort of. The core idea is that maybe all the information describing a volume of space, including gravity within it, can actually be encoded on a lower dimensional boundary, like the information for a 3D image stored on a 2D holographic film.
Whoa! So gravity in 3D space could be described by quantum physics on a 2D surface.
That's the essence of it. It suggests a deep, maybe unexpected connection between gravity and quantum field theory. It's seen as a key property any real theory of quantum gravity would likely need to have.
Okay, that's pretty mind-bending. But how do they test it? I thought the problem was we couldn't experiment at those scales.
Exactly. You can't build a lab to probe the Planck scale or create the energies needed. So as Professor Varela points out, for theoretical physicists, their tools are different.
The math.
The math. Precise mathematical models become their apparatus. They use these models to explore possibilities, make predictions, test the consistency of ideas. It's theoretical experimentation.
So these complex equations are, in a way, they're experiments.
In a very real way, yes. They're building theoretical structures based on principles like holography. And their recent paper in Physical Review Letters, published May 6th, 2025.
Ah, you have the details.
It's titled Class Superconformal Indices from Maximal Supergravity. It really dives deep into the mathematical connections suggested by the holographic principle, specifically within supergravity, which is like general relativity, plus another layer called supersymmetry.
Okay, so the paper is them using this holographic framework to build these mathematical models.
And testing if the connections hold up, looking for consistency, trying to see if this path leads towards a unified theory. They're pushing the boundaries of what we can calculate and understand theoretically.
Got it. So the big picture here is we have two great theories. They don't work together. Direct experiments are basically impossible right now.
Right.
So this team at Utah State is using this holographic principle idea as a guide to build mathematical models, hoping these models will show the way to finally connect gravity and quantum mechanics.
That's the core of it. They're using these theoretical tools, these mathematical structures, to bridge that gap, tackling one of physics' biggest outstanding questions.
It really makes you think, doesn't it?
Absolutely. And here's something for you, the listener, to ponder. Imagine we did find that unified theory. If we could finally describe gravity and quantum mechanics with one single voice, what would that actually mean for how we understand reality?
Yeah, what fundamental shifts would happen in our view of the universe itself?
It's a profound thought, a potential revolution in understanding everything.